Hello friends, welcome back to Urban Academy. In the last lecture, we have completed the discussion on the constraint motion. So in this particular lecture, we will start discussing work energy and the impulse. So the first topic that we have to discuss under this is Hooke's law. So what is the Hooke's law? The statement is the tension of an elastic string is proportional to the extension of the string beyond its natural length. So what is the statement of the Hooke's law? The tension is proportional to the extension of string beyond its natural length. Okay, so on removing this proportional sign, we have the tension as is equal to lambda into extension upon natural length. Okay, so for understanding this, let us consider an example. So let us consider a string of natural length L. Okay, let us extend this to a distance of x from O. Okay, so what is our extension? So the extension is this one. This is our extension. The extension is x minus L. And this is our natural length. So what we are having, the tension is equal to lambda into x minus L upon natural length. This is our tension. So the tension is equal to lambda into x minus L upon L, where lambda is the modulus of elasticity. Okay. Suppose we have to find the tension at this particular point. Suppose it is further extended to a distance of y. Okay. So let us take this as a. It is further extended to a distance of a. So what will be our tension at this particular point? Let us name this as uh, let us name this point as O. This is A. This is B. So the tension at point B is equal to extension is, this is our natural length. So with respect to the natural length, the extension is this one. Okay, this is our extension. So the extension is A minus L. So what will be our tension? Lambda into extension. Extension is A minus L. Okay, upon natural length is L. So this is our tension at point B. Okay, so let us move further. Okay, so we have the work done in stretching the string beyond the natural length. Okay, so we have the work done against the tension in stretching a light elastic string is equal to product of its extension and mean of the final and initial tension. So let us consider a string of natural length A. Okay, so it is extended further to a length of B and C. This is extended further to a length of B and further extended to a length of C. Okay, so what is our extension? So let us name this. This is O, this is A, this is B and C. Okay, so the extension here is this one. Extension is BC and the extension is C minus B. Okay, and initially the tension at point B is, let us name this as Ti, initial tension, and the tension at point C, this is the final tension. So the work done in stretching the string from B to C is given by work done in stretching the string to B to C is equal to, this is extension into initial tension plus mean of initial and final tension upon 2. This is equal to, extension is C minus B into Ti plus Tf upon 2. Okay, so Ti is tension at B and Tf is tension at C. Okay, so let us start discussing problems on the Hooke's law. What is the first question? Prove that the work done against the tension in stretching a light elastic string is equal to the product of extension and mean of its initial tension. Okay, so basically this is the proof of this statement that we have studied. Okay, so let us prove this. So we have, let us take a string of natural length A. Okay, it is extended further to a length of B and C. Okay, let us name this. This is O, this is A, this is B and C. So we have the, from Hooke's law, tension at point B is equal to lambda into extension. The extension is B minus natural length upon A. A is the natural length. Tension at point C is equal to lambda into C minus natural length. So this is A upon A. This is tension at point B. Now let us consider a point P here. Okay, let us take a point P here that is at a distance of x. That is at a distance of x from O. And let us further take a elemental extension dx. Okay, this is our elemental extension dx. So the tension at point P is equal to lambda into x minus natural length upon A. This is our tension at point P. Okay, so what will be the work done in stretching the string to a elemental distance dx? So work done in against tension in stretching the string for elemental distance dx. So the work done is equal to dp into dx, and the integration is from, we have extended the string from b to c. So we have here we have x is equal to b, and here we have x is equal to c. So the integration is from x is equal to b to x is equal to c. So this is equal to b to c, and dp is lambda x minus a upon a into dx. So let us integrate this. So what we are having is work done is equal to lambda upon a x minus a whole square upon 2, and limit is c and b. So we have lambda upon 2a c minus a whole square minus b minus a whole square. This is work done. Let us further simplify this. Let us further simplify this. So we have work done is equal to lambda upon 2a into, this is a square minus b square. So we have a minus b into a plus b. So we have c minus a minus b plus a, okay, into c minus a plus b minus a. Okay, so this gets cancelled. So we have w is equal to, work done is equal to lambda upon 2a into c minus b into c minus a upon a plus b minus a. Okay, this is not a. Okay, so let us further simplify this. So we have work done is equal to um, c minus b to half. We have lambda. Let us take this term. B minus a upon, this is a here. So let us take a here plus lambda c minus a upon a. So this is our tension at B, and tension at B is the initial tension. We can write this as, and tension as T is final tension. Okay, so we have W, and extension is, so this is our extension, B to C is the extension, and extension is this one. And this one is C minus B. The C minus B is extension. This is extension into, and this is Ti and this is Tf. So we have Ti plus Tf. So we have work done is equal to extension into mean of initial and final tension. Final tension. Okay, this is our work done. So let us discuss question number 2. Okay, how we can solve this? So we have a light elastic string whose natural length is that of a uniform rod. Okay, so this is our uniform rod. Okay, and this is point O. Okay, be attached to a rod at both the ends and suspended by the middle point. Okay, so this is our middle point. So let us take light elastic string. Okay, and here theta is equal to 0. There is no inclination of the string with the horizontal. Theta is equal to 0. So this is suspended like this at both the ends and suspended by the middle point. So this is our middle point. point. Show that the rod will descend until each of two portions of the string is inclined to horizontal at an angle of theta given by the equation. So basically we have to prove this expression, okay? And the modulus of elasticity is n times the weight of rod. So let us consider the mass of this rod as m. Mass of this rod is m, so the weight is mg. So we have lambda is equal to nm. So let us drop this. So what will be the final position? So let us consider this. This is the position of the rod at the inclination of angle theta with the horizontal. Inclination of string with the horizontal. Okay. So this is our final position of the rod. Okay. So we have the inclination as theta. So this is our distance is a. This distance is also a. Okay. So here the tension is equal to 0 because it is in this position. Theta is equal to 0 here. Okay. And now this is with now the let us consider the tension at the final position as tension at the final position is tension and final position is T. Okay. And we have this as A. So this distance will be A tan theta and this distance will be A sec theta. This is also A sec theta. So what is our extension? So extension is equal to total length of the string is final length of string minus initial length. This is equal to 2A sec theta minus 2A. This is our initial length is 2A. This is equal to 2A sec theta minus 1. This is extension. So the tension, final tension is equal to lambda into extension upon natural length. So this is equal to lambda into 2A sec theta minus 1 upon 2. This is lambda sec theta minus 1. Our work done is equal to extension. The extension is 2A sec theta minus 1 into half of initial and final tension. So 0 plus lambda sec theta minus 1. Now the work done is equal to the descent, the height with which the rod is descended is A tan theta, and total work done will be mg into A tan theta. Okay. So we have mg into A tan theta is equal to 2A into sec theta minus 1 into half of lambda sec theta minus 1. So this gets cancelled, A to A cancelled, and we have lambda is equal to nmg. This is equal to nmg into sec theta minus 1 whole square. This gets cancelled. So we have tan theta is equal to n times of sec theta minus 1 का whole square. Let us further simplify this. Tan theta is equal to n times of sec theta minus. So we have tan theta is equal to n times of sec theta minus 1 whole square. So we have sin theta upon cos theta is equal to n times of 1 minus cos theta whole square upon cos square theta. This gets cancelled. So sin theta cos theta is equal to n times of 1 minus cos theta whole square. This we can write as 2 sin theta by 2 cos theta by 2 into cos 2 theta we can write as cos square theta minus sin square theta. So this we can write as cos square theta by 2 minus sin square theta by 2 is equal to n times of, and 1 minus cos theta is equal to 2 sin square theta by 2. So this we can write as square of, so 1 minus cos theta whole square is equal to square of this, so 4 sin 4 theta by 2. This is 4 sin 4 theta by 2. Okay, so this gets cancelled. This is 2. So we have this as this gets cancelled. So this is sin cube theta by 2. So we have this as cos cube theta by 2 minus cos theta by 2 into sin square theta by 2 equal to n times of sin cube theta by 2. This we can divide by this sin cube theta by 2. Okay, so this we are left with n. Okay, so this is equal to cot cube theta by 2 minus cos theta by 2 or upon sin theta by 2. This is cot theta by 2 is equal to, here 2 is there, so this is 2n actually. This is equal to 2n. So this is the um, required expression that we have to prove. Okay, so let us discuss question number 3. Okay, so a cylindrical cork of length L and radius R is slowly extracted from the neck of a bottle. So let us draw a bottle like this. This is our bottle, and there is a cylindrical cork. Let us draw the cylindrical cork. This is a cylindrical cork of length L, and let us analyze this with a the inserted part is x. Okay. Also, let us take a elemental strip of length dx. Okay. So the area of contact for the x length of the cork. So the area of contact for x length of cork. For x length of the cork, what will be the area of contact? This is 2 pi. The radius is r. Let us read this. The cylindrical cork of length L and radius r is slowly extracted from the neck of a bottle if the normal pressure per unit area between the bottle and the unextracted part. So this is unextracted part. Unextracted part of the cork at any instant be constant and is equal to P. Okay. So that the work done in extracting it is pi mu r L square P, where mu is the coefficient of friction. The area of contact for x length of the car is 2 pi r into x. This is area of contact. Area of the contact. So we have the force acting on this surface is equal to pressure into area. So we have 2 pi r to x into pressure. Okay, so what will be the frictional force? So frictional force on this will act in bottommost direction. Okay, because the movement is in this direction, so the frictional force will act in this particular direction. Okay, so the frictional force will act in this particular direction. So the frictional force is equal to mu times of normal force. So the normal force is 2 pi r x into p. So we have mu into 2 pi r into x into p. This is the frictional force. Okay. So the work done will be in extracting the cork to a distance, elemental distance dx. This is the elemental distance dx. Elemental distance dx is equal to f into dx, which is equal to mu into 2 pi r to x into p into dx. Okay. And we have to extract the whole cork. Okay, so the limit will be x is equal to 0 to x is equal to L. So the limit will be 0 to L. So let us integrate this. So we have 2 pi mu r into p into L square upon this gets cancelled. So this is equal to pi mu r L square into p is the work done. Okay, so let us discuss question number 4. So what is given in question number 4? Prove that the work done in stretching an elastic string AB. This is our string AB. Okay, and in work done in stretching an elastic string AB of natural length L and modulus lambda from tension T1 to the tension T2. Okay, let us consider the stretched lengths as L1 and L2. These are our stretched lengths. So we have stretched the string to a distance of C and D. So we have the stretched lengths as L1 and L2. Okay, so we have AB is equal to L, AC is equal to L1, and AD is equal to L2. Okay, and this is our natural length. And as per the question, the tension at point C, that is when the stretched length is L1 is T1, and the tension at point D when the stretched length is L2 is T2. So from Hooke's law, the tension at point C is equal to T1 is equal to lambda into the extension is BC. This is extension, and with respect to L2 we have the extension as this one. So the extension um, here is from B to C. Okay, when the stretched length is L1, the extension is L1 minus L, and when the stretched length is L2, the extension is L2 minus L, L2 minus natural length. So from Hooke's law, we have Tc is equal to tension at point C is equal to T1 is equal to lambda times of L1 minus L upon L, and tension at point D is equal to T2 is equal to lambda times of L2 minus L upon L. Okay, and as per the reductions from the Hooke's law that we have already studied, the work done in stretching the string from C to D is equal to extension. The extension is CD. So this is CD into mean of initial and final tension. Okay, so we have initial tension as tension at point C, that is T1, and final tension is T2. So T1 plus T2 upon 2, and CD is equal to L2 minus L1. So this is equal to L2 minus L1 into T1 plus T2 upon 2. Okay, so from here we have, let us subtract, this is equation 1 and this is equation 2. So equation 2 minus equation 1. So we have this as lambda upon L. This is L2 minus L1 minus L1 plus L. Okay, this is equal to T2 minus T1. This gets cancelled. So we have L2 minus L1 is equal to L upon lambda T2 minus T1. So let us place L2 minus L1 here. So this is equal to L upon lambda T2 minus T1 into T1 plus T2 upon 2. This is equal to L upon 2 lambda into T2 square minus T1 square. This is work done in stretching the string from C to D. Work done. Work done in stretching the string from C to D. That is from tension to tension T2. From tension T1 to tension T2. Tension T1 is at the position C and tension T2 is at the position D. Okay, so let us discuss question number 5. A motor car weighing 10 quintal. Okay, so the mass is equal to 10 into 1 quintal is equal to 100 kg. So this is equal to 1000 kg and traveling at 12 meter per second. So the initial velocity is equal to 12 meter per second is brought to rest in a on 18 meter by the application of brake. So obviously there will be some retardation. So let the retardation is r meter per second square. Okay, so we have the equation of motion is final velocity is equal to square is equal to u square plus 2as. So since there is retardation, so we have negative sign here. So v square is equal to u square minus 2a into s. So we have the since it is stopped by the application of brake, so the final velocity will be 0. So 0 is equal to initial velocity is 12. So 12 square minus 2 into r into and it is brought to rest in a distance of 18 meter. So we have R is equal to 12 into 12 upon 2 into 18. So this is 6 3 18. This is 4 meter per second square is the retardation. Okay, so we have the frictional force as frictional force, work done by the force of resistance. Okay, or force of resistance. Force of resistance. Force of resistance is equal to mass into acceleration. Mass into retardation we can write. There is no acceleration here because the velocity is getting decreased. Mass into retardation. So this is equal to mass is the 1000 into 4. This is 4000. This is force of 4000 Newton. Force of resistance. Okay, so the work done is equal to force of resistance. Force of resistance into um, distance traveled. Distance traveled before coming to rest. So this is equal to 4000 into distance traveled before coming to rest. This is 18 meter. 18 meter is the distance. This is Newton. So we have this as 18 into 4. This is 72,000 joule. Okay, is the work done by force of resistance. Okay, so we have discussed up to question number 5. Okay, so we will discuss further topics in the next particular lecture. Thank you.